Thank everyone for watching the talks today. And I will take this opportunity to introduce our three speakers, Jeroen Haviv, David Aronczyk, and Greg Hayes. So Jeroen is CTO and co-founder of the data science platform Iguazio. David is partner at the office of the CTO in Azure and works on MLOps on the next generation of ML technologies. And Greg is head of data science at Ecolab. So today they will share basically Ecolab's journey with MLOps. So Ecolab's, for those who don't know, is a global hygiene technologies provider. They will show how they build a cutting-edge cloud data science architecture, which enables them to deploy new AI services every 30 to 90 days. So please give a warm welcome to Jeroen, David, and Greg.
So hi, everyone. Thank you so much for the opportunity. I am David Aronczyk. And it's wonderful to talk about a real-world scenario in which people transition to the MLOps journey and some of the challenges that they face along the way. So, we've been, all three of us have been out, talking about MLOps and GitOps for quite a while. And I would say the number one story we hear is this one. This tweet came from 3 years ago, and every time I present it, the entire room shakes their head yes and says, 11 months, that seems short. The challenge in moving from your code, from a working notebook into production remains just as big as today as it was when this tweet was sent. And unless we take real action, it's going to be tough to do even into the future. And some of the reasons that we see that it is so difficult is what you see here. Oftentimes proof of concepts are very far off from what you need to do when they're in production, kind of the classic, it works on my machines. Oftentimes the handoff between the data science organizations, the SRE teams, the ML teams is very challenging. AI is obviously really valuable, but there's still a really big gap between how it's the stories, the news stories you see every single day, and what actually gets used. And it is definitely not for free. Some of the more detailed hurdles we talked about, I already mentioned, working in silos is probably one of the biggest problems. And that's not just silos for people, it's silos for tools. For better or worse, a Jupyter Notebook does not produce a production artifact, even though everyone uses it and it's wonderful for development. There's a lot of transition, and those silos require different skill sets, different tools, everything along the board. It's also can be very, very resource constrained. It is not at all uncommon for even moderate-sized models to take many hours or days to train, and that cycle which happens so quickly on your laptop can often take a long time. The access to data is incredibly valuable, and certainly one of those things that you want to enable, but there are many restrictions, the geo restrictions, security restrictions, and things like that. So many features that you might use to train on are not immediately available, and that can be challenging as well. And then of course the final thing, which I think a lot of people get anchored on, is model accuracy. And it's not just model accuracy when you train, but it's model accuracy over time. Machine learning models, unlike many things in technology, suffer from real rot, which is uncommon. So something that worked yesterday may not work tomorrow, and so on. There's a wonderful paper that Google actually published about 5 years ago called "The Hidden Technical Debt of ML Systems," where they detail many of these things in more detail. I already mentioned several around drift and things eroding based on data changes, based on things like that. There are lots more in there, and I highly recommend reading it. But a way to detect that you are already in the drift mode is the extent to which you are writing handwritten Bash or Python or Go scripts to convert or move from one step in the process to the other. A real system that is maintainable over time is one where you check everything in at the left-hand side and then use nothing more than 12-factor to shift things along the way. And you can see some of the concepts of 12-factor using environments, pipelines, so on and so forth. So, at the end of the day, we think that the way around this is through, XOps, where you substitute X for one of these many things. Could be data, having, declarative pipelines for processing your data, creating features and things like that. MLOps, which we'll certainly talk about today, for moving your entire system through the pipeline. Model ops, once your artifact has been created, how do you roll it out? How do you track it when it's been embedded in an application? How do you, to track exactly what that user's experience is? And then AI ops, looking at the way that your model is operating in production, ensuring that it's, providing the correct telemetry, using the proper resources, and remain secure. And with that, I'd like to hand off to Greg.
So can you see my screen? Hello?
Yeah.
Okay. All right, great. So a little bit of background. As was mentioned before, I'm the Director of Data Science at Ecolab. Ecolab is the global leader in water hygiene and infection prevention solutions. We partner to make the world cleaner, safer, and healthier, helping customers succeed while protecting people and vital resources. I lead the functional teams at Advanced Analytics. In practical terms, that means I'm responsible for data science technology platforms and standards. So with that in mind, what we want to talk about today is how data science seems to evolve, effectively my view of how data science seems to evolve within many organizations, and to share some thoughts on how we can accelerate the creation and the deployment of machine learning enabled solutions. So how does data science get started in most organizations, in my experience at least? We have subject matter experts or maybe emerging data scientists. They have a problem that they know that needs to be solved, and they go through this process where they have a hypothesis, they find data, they clean it, they schematize it, they get to something that looks promising as a model, kind of an initial candidate. And they've done all this work, and it's great work, but it's happened without any real engagement from many of the stakeholders that are needed to integrate this model into some sort of a product so it can be consumed. A model is not a product in and of itself. A model is one component of an overall product. And to get that component integrated, you have to have security, data engineering, front-end development, networking, product owners, finance, all of the different stakeholders. So what happens is they work on this for a while and they try to get buy-in, but eventually they get frustrated because the process of creating a product is really constrained by portfolio management. That is, how does work within an organization get prioritized and resourced? And since this work's happened in isolation, nobody really knows. So as they get frustrated in this process, they say, well, we're just going to make the model better. So they get in this loop, this consistent loop of trying to improve the model performance, but they never actually get to a product. So then as we go through this process, the data science teams start to mature, and so do the organizational processes. We eventually get to the point that we form a cohesive organization. Maybe we have data engineers, scientists, SMEs, the experts. They organize to try and solve some well-defined business problem. Oftentimes, maybe they've talked to a customer, maybe they haven't, but they're pretty sure they've got a problem that they can solve that adds value. So they resource it. The data scientists, they go through, they create their hypothesis, they clean, they schematize the data, do the feature engineering. This is a loop, right, where they iterate on the quality of the model, but they've got engagement from the stakeholders. They have a clear path to create a product. And as they go through this iterative process, eventually they get to a model that looks promising, and they hand it off, the dreaded handoff, and then the software engineering team takes over and they do a rewrite and deploy. So this is great. We actually get value. We get it in front of the customer. We derive business value. But unfortunately, creating digital products, or maybe in a kind of a newer world, any products, is an iterative process. And the model is part of that, part of the process that has to be iterated on. So what happens when we need to make adjustments, right? To David's point, models rot, or we need to improve the model performance, right? To better meet customer expectations. This loop is a one-way loop, right? There's no way to iterate directly on the model because we've changed languages. We've not taken what was done by the data scientists and deployed it. What does this look like from a GitOps perspective? Well, so we have an isolated team of data scientists, and we say, well, the data science team can work on whatever tools or processes they want on the left-hand side of the box. They're typically working, they're prototyping and training, building models on static data. It's not connected to what's being run in the real world. Hopefully they are using Git, but so you create a user story, topic branches, perform EDA, and eventually you get to a model that looks promising, and you have this green box on the left-hand side that's feature vector specification. Right, so in the ideal state, the model that's written is actually what gets deployed for consumption, and then we check this over the wall to the software engineers with a spec, and then they effectively rewrite some or all of this pipeline to deploy this model. So this really contributes to very long lead times and introduces many points of potential failure because we've changed languages, and does every language implement each step the same? Right? There's no connection, direct connection between what the data scientist has done and what the customer eventually sees. So as these gaps get recognized, right, teams start looking for ways to address them. This creates a desire to implement an iterative approach, and I think most people who are involved in MLOps are familiar with some version of this, with maybe a few tweaks. In this model, we start by putting the customer at the center of the process. So we're going to borrow from the best practices of software engineering and user-centered design. Sure, we need to provide tools and processes to facilitate it, but let's start with the higher level goals. Right? We want to facilitate collaboration. We want to engage our customers and our stakeholders right from the outset by integrating the activities of data science directly into product development. Our intention is to create a direct connection between the code that the data scientists write and what the customer sees, and be able to iteratively develop, right? So what do we do? Well, we leverage agile development. We have user stories that have clearly defined deliverables, and they're time boxed, right? We want to provide a forum through agile to address blockers and risks so that stakeholders they're aware of what's going on, and subject matter experts and business owners can help us address these concerns to better add customer value. We have clearly defined deliverables. All of this is with a goal of reducing the time from concept to product so we can create customer value faster and iterate on it to optimize that value. A few other things another thing, I guess, I suppose, that we want to think about is how we approach the idea of models. In that first version of our workflow, the focus is really on how do I build the very best model, right? You want to build the race car. And in that process, it really extends the time to add customer value. This is borrowed directly from Building Machine Learning Applications. It's a great book, but the interesting thing is, right, we want to start with simpler models, right? And iterate on those models to improve upon them and add value, right? But again, the goal is to get to customer value quickly. A few things that help facilitate that. If we're working with flat files, we want to use Parquet. We've seen a lot of examples where we use CSV files or text-based files. They're large. There are many challenges associated with working with them. So we try to drive toward leveraging Parquet files. We want to version our data and our models together for traceability and maintainability, some of the best practices we pull into play. And finally, we want to consider model serialization early. If you're building a model and you discover that model is going to be deployed on something like a wearable device that doesn't have the compute that you need to run it, then you're stuck, right? So this is, again, one of the components of understanding the deliverables. So let's take a quick look at some of the tools that are emerging to support this MLOps process and facilitate this collaboration. On the modeling and the exploration side, there are libraries that most data scientists know and they love, particularly for in-memory compute. We have this additional competency, and that's the ability to run code against any data set. So, most of the in-memory compute we can handle pretty well. For distributed compute, when data sets get larger, we can move to things like Dask and Spark. One of the gaps when we attempt to scale data science, right, is provisioning scalable, secure compute. We don't want to have each individual data scientist working in their own VM in isolation because those aren't going to scale. How can we facilitate that? Some of the newer open source projects like Kubeflow and Metaflow, Google and Netflix respectively created those and open sourced them. They enable collaborative data science in containerized environments, right? So a data scientist can get a notebook. They can request compute resources on demand from that shared cluster. Dramatically simplifies and reduces the time to deploy and provision resources. On the artifact tracking and logging and versioning, right, we have Metaflow, MLflow, MLrun. They're all emerging because regulatory requirements around traceability, reproducibility, and explainability of ML models. This is becoming more and more prominent as time goes on. Tools like this are enabling native logging of machine learning artifacts like data sets and outputs. Cloud providers are also creating tools inside of their ecosystems, but it is a requirement. Finally, how do we go to automation? Right, we want to directly deploy our code. We want to create a direct link. Workflow scheduling tools like Apache Airflow, Kubeflow, Prefect, and MLrun in combination with Kubeflow pipelines, they enable direct execution of, or the creation of workflow scheduling pipelines, which facilitates, again, that direct connection between what the data scientist is doing and what the customer sees. And the foundation for all of this becomes these collaboration and testing tools. Get Azure DevOps, Azure pipelines. We want to drive CI/CD. So given all this as a goal, what might a code development workflow look like? If we start from something like a Kubeflow type environment where we have a containerized environment, the first thing that we do is we give our data scientists a Jupyter notebook. They have a fixed set of resources, they're readily available, and they can start doing their exploration inside of an in-memory compute environment or distributed if necessary. But oftentimes we start in memory. They do their exploration, they do their prototyping. As they go through that process, they're creating functions, and those functions eventually become hardened. Once those functions are hardened, then we ask them to refactor that code out into pure Python files. Now, why do that? First of all, it enables us to leverage best practices from software engineering. We can lint and test our code, and then we can also import those Python modules and share them across users, so that we can identify and capitalize on the patterns that are common across many projects and problems. They go through this loop, and then they may decide that they're ready to scale up or scale out, rather. So they can then take that code, they can leverage tools like Spark and Dask, and again, refactor those pure Python files, but with an eye toward distributed execution. This also gives us the opportunity to capitalize on something like MLrun to create Kubeflow objects that we can run directly or remotely as part of a pipeline, and we can log those artifacts. Once we have those MLrun objects, then those can be orchestrated through Kubeflow pipelines, and we have the opportunity for integration. This also loops back, so we can take those pipeline objects and those MLrun objects, and we can iterate on them. So this allows us to leverage CI/CD for our deployments. What does this look like from view through the lens of a GitOps-based workflow? So again, oftentimes we see that source control is sometimes new for data scientists, but we start with a Git branch. We're working in an agile environment. We're leveraging Azure DevOps for collaboration. So working with our partners, we create a user branch or user story and a topic branch, And we start doing EDA inside of the Jupyter Notebook. We push regularly. As that EDA starts to resolve into more robust Python functions, we refactor those out into pure Python files, and those get imported into notebooks. From there, we can issue a PR. And if we've written unit tests, we can automatically run those unit tests and lint our code. As those become more mature, then we can start to leverage ML run functions and refactor for scale-out monitoring and retraining. This is effectively an integration point between the activities of data science and machine learning engineering on the right-hand side. Those functions can then be tested for creation of Qflow pipelines and experimentation. Again, we can issue those as PRs. This all resolves back into Git through pull requests. We can leverage then the best practices from Python. We can tag a release. And once that tag is created, then we automatically build and release to a dev environment, and again to a prod under service accounts, because we want these to be production grade systems. We don't want to be running under data scientists' individual user accounts. A few guiding principles. We want to separate development and production environments. We want to have a sandbox that our data scientists can prototype in, and also release to for prototyping that is isolated from production. We want to check our code into source control, and that allows us to implement continuous integration. We can automate the linting and testing of our code. We want to validate with our stakeholders, does our model or our update to the model meet the business requirements? We want to create automated continuous deployment pipelines, and we want to deploy our models under service accounts. We do not want in a production environment for our models to be linked directly to an individual user. We want to engage in incremental development, and we want to monitor the performance of our models over time in an automated way. And we also want to enable incremental releases into production. How do we think about enabling success for the teams? First, we want to leverage Agile and Scrum. We start by creating PBIs or user stories to drive communication and clarity with our stakeholders. We want to document and share requirements, make sure that everyone understands the expectations, and communicate RACI. Make sure everyone understands what they need to provide and what you need from them and what they need from you to be successful to build a digital product, not just to build a model. We want to collaborate with our internal and external peers and stakeholders through these PBIs, and then we want to link those PBIs or Agile stories into Git branches. As we think about getting started in a project, we have this prototype and develop phase. First rule, put our code in Git from day one, push daily. We want to make certain that we align the model metrics to the business objectives and document those inside of the user stories. We want to make certain that we include a benchmark for our models. In many examples or many cases, there is some sort of a model that exists for the work that's being done. It might be a subject matter expert heuristic, but there is some benchmark for the models that we're creating. We want to balance performance versus complexity and speed. We choose to prefer Apache, MIT, and BSD packages for clarity about expectations. As we go through the prototyping developing process, we said, refactor common functions, import them, and share them. Another potential catch point is prefer fitted transformers where possible to prevent data leakage. Methods like get dummies, unfortunately pandas get dummies, unfortunately does not work when you're passing in production new data, because you have to be able to basically recreate the feature table. We asked our data scientists to PyTest those critical functions, create unit tests to validate that the code performs as expected. They are the experts in this case. And lint our code for readability. We want our data scientists to be able to move between projects when necessary, So they have the opportunity to work on new things, and the organization can better support the models as they go to production. And then automate integration testing so that this is not a manual process. As we go into our engineer and iterate steps, we want to leverage ML run objects for remote execution, and then document the solution architecture. Everyone needs to have clarity on where the data is sourced from, how the process occurs, and where the data should be landed. As we go through of our models, we're going to start with in-memory compute, and then we will scale our work out. As we consider how to scale that work, we start by reducing memory usage to optimize. Then we start considering how to vectorize operations. We want to eliminate things like long-running for loops. And then last, scale out. Distributed compute is very effective. It's very efficient, but it's also complicated. If we don't need it, let's not use it. And then really, this is where we're going to get into the software engineering piece. Reuse our existing patterns and code where possible. In an ideal world, we don't want every data scientist writing a unique method or function to create a connection to a SQL database. Let's leverage those common patterns and codes and help them accelerate their work. Log artifacts. This is the traceability piece. We want to develop a monitoring and retraining strategy up front, document it, make sure that everyone is clear on the requirements. And then secrets, some of these others are best practices. What are the benefits? The greater collaboration, the collaboration that you get from working in an agile environment is huge. All of your stakeholders clearly understand what you're trying to deliver. They understand what they need to do to facilitate that process, and you understand what you have to provide so that your model can make its way into production. The process of leveraging the same code that goes from proof of concept to development to production, it improves the reproducibility. You have that direct connection, and it reduces the time to product. As I said before, we've gone from 11, 12 months to deploy down to as short as 25 days in some cases. We want to leverage those best practices from software engineering to improve maintainability of our systems, and we want to have scalable solutions. We end up with scalable solution processes to support our customers. And with that, I will turn it over to Yaron.
Okay, I hope you see my screen.
Yes.
Good. So Greg did mention MLRun a couple of times, and what I want to show is first, how do we sort of structure all this sort of MLOps in one framework, or with the help of a lot of different open source tools. And also I'll show a demo of sort of building a fully operational pipeline. But before we dive into the demo of how to build that operational pipeline, one of the things that we did in Iguazio is essentially, and also, by the way, some of the background is work with Greg and David on defining the requirements, was building a stack that essentially tries to consolidate all of those different steps into one tool that orchestrates the different other frameworks or open source tools. And we layered it in a few layers. The underlying layer is what we call the feature store and data connectivity. Everyone knows that the core challenge in machine learning is really dealing with the data. So we'll touch upon it in a minute. The second is we need to execute jobs. We need to execute services for model surveying, for data ingestion, for many different things. And we figure out that one of the best ways to simplify this job execution, if people start with a piece of code in Python or other languages, and you want to turn it into sort of an elastic managed service which gets monitored and logged, etc., is essentially use serverless technologies. And we're going to see how it's working. And those serverless technologies essentially allow you to throw in some piece of code, and that piece of code will get into a container that auto scales, that manages its resources, that you can track its activities and track all the inputs and outputs that get into that thing, and so on. On top of it, you have a set of services that build on those two components, on the serverless processing engine and the feature and data connectivity. And those are segmented to the 4 things that you need to do in a pipeline. So first is data ingestion and preparation aspects. Then we have the model training and testing, essentially building those development pipelines. Third is building the operational pipelines, the one that actually work and get data in real time or from operational data stores, runs inferencing and so on. And finally, we also need to analyze the model behavior, the data patterns and so on, and identify anomalies, drift, inaccuracy, and so on. So we've essentially put everything under one stack. And the philosophy, again, in terms of development, is enabling what Greg was talking about, sort of more of a continuous development workflow across teams. So we don't want the data scientists to work on a Jupyter notebook and then sort of throw it over the wall, and someone else will take that Jupyter notebook and refactor it as a microservice or as a container or managed service. This is a very long and tedious job, and every time you need to change a piece of code, you have to redo the entire ritual again and again. So the way that we want is to build it is sort of more of a continuous flow, where you write a piece of code in your native environment, whether it's a Jupyter notebook or an IDE like PyCharm or VS Code. You want to test everything within your native environment, put breakpoints, debug, and test. When you feel you need a little more scale, maybe resources like GPUs, lots of memory, access to fast data, and so on, you run the same job in a containerized workload. But in order to move from your notebook into a containerized workload on a big cluster, it's a single command, essentially something we call code to function, which will launch your workload on a distributed cluster anywhere you want. Once you finish debugging and creating this microservice, you can store it in a marketplace and then build workflows for like building a multi-stage pipeline, like bringing data, running training, running evaluation, selecting features, doing some deployment of the model and testing the deployment, and so on. And maybe we also build operational pipelines that run in real time, listen on streams, gather data, and so on. And all of those workflows needs to be monitored. Things like experiment tracking or real-time monitoring of the service need to be applied as much as possible through automation. And again, we want to have as much reuse as possible, so when we develop in our notebook or our environment a feature, the feature is a definition. It's not just the data, it's sort of a definition of an ETL pipeline or a real-time pipeline that transform data from from raw data into sort of a meaningful feature. We want to store those features and use those features in different applications and different pipelines. So with that process, we get something which is more continuous. You develop in your native IDE, you test on a cluster, you feel it's ready, you build a more advanced pipeline with automation and CI and so on, and you track everything and you can sort of go back and forth. With that, I'll show you a demo, but before looking into the demo, the different things that we need to do in a real operational system, starting again with the data. So we need to collect data. Everyone is used to having data as CSVs and Parquet files already sitting and waiting for the work. But in reality, that's not the case. Data will arrive from operational databases, from logs, from web APIs, from streams, and so on. So in this demo that I'm going to show you, we're going to look into a predictive financial application, fraud prediction application with some simulated data. So the data that arrives to that fraud detection is coming from different sources. For example, the actual transactions of the consumer, the credit card holder, different account activities like logging in, logging out, changing password, and so on, and other data that's associated with the user, potentially gender or age or other things that may enrich our model. So we want to feed all of those into what is referred to as a feature store. It's essentially a place that catalogs all the different features. It's first generating the features using analytics pipeline, real-time or batch analytics pipeline using different tools. then storing and cataloging those features in a feature store. We can go and do interactive development and exploration on those features. Once we feel that the features are ready, we need to build applications. The first thing that we need to do is the model development pipeline. It's essentially feeding data and doing some exploratory data analysis. In some cases, running feature selection and preparation. So essentially choosing the right features or filtering features that may not be as useful, running the model training and evaluation and so on to verify that we have a model. If it's not a good model, again, we may iterate and bring more features or change our parameters and so on. And then we have a model. Once we have a model, we want a pipeline that uses the model. It's a different pipeline. It's not the same pipeline. The other pipeline will essentially intercept, listen on, for example, an HTTP endpoint or a real-time stream. It will intercept a user request. We'll throw that user request through an API. We'll have to enrich the data from using the feature store, the features that are in the feature store. For example, I get the user ID, and I want to have all the features associated with that user. So we may do enrichment here, potentially other things like anomaly detection, validations, and so on. Then we serve that model through a model serving layer. And in some cases, it's more than one model. And I'm actually going to show you that I'm using an ensemble. And finally, when we have the model result, we need to respond to the application, again, through HTTP response or by throwing the result into an output stream. But we also have the model and data monitoring. So we want to monitor the activity of our model, see if there is a drift or another problem, and potentially retrain the model by essentially triggering the model development pipeline to rerun with fresh data and so on. So this is how sort of a more of an operational system works. And you can see there's a lot of different pieces that you need to build. I'll try and do it in a simple way. This is what usually takes a year. We'll try and do it in a few minutes. So let's go into my notebooks. So the first thing we mentioned that we need to do is essentially go and create the features. So we have different data sets. We have customer transactions, we have customer events, customer transactions, and so on. And we want to go and ingest all of those from an operational system. So using the MLOps tools, we can just create ingestion pipelines in a relatively easy way. Let's assume that we have some test data in like S3 bucket somewhere. This is how the transaction data looks like. You see for every user, you have transactions, type of transactions, and so on. We want to define essentially a feature set. A feature set is a set of features that get ingested together, have sort of the same entity, and so on. So in order to build that pipeline, I'm essentially creating a feature set for the transactions. I'm building a pipeline. This pipeline have to do data extractions and aggregates, essentially taking from the features, turning the data into something meaningful, like hour of day or a day of week, etc. Building aggregates, because if you have a stream, usually the feature is something which is aggregated, like a number of transactions in the last week or the last hour. So here I can essentially just define a pipeline, define data extractions for hours and days a week, define some aggregates for average sum and so on for the transaction amounts. And then I built a pipeline. I can just simulate my pipeline in my notebook. And once it's ready, I can just go in and deploy that analytics pipeline into production. We can do the same for other types of data, like this is the event data, showing that for every customer logins, logouts, password changes, etc., that may add indications to fraud. So this data, because there are different types of transactions, we want to do one-hot encoding and potentially other transformations. So we can build another pipeline for the events which have some one-hot encoding in this case. And here's the new feature set that we've created, which is transforming the input data to an encoded data. We may want to do other things, like especially like in fraud analysis, it's very different. If you buy, if you go to the groceries, you probably go every day or every few days the supermarket, you don't buy shoes every other day, unless you're my wife, but that's a separate topic. And so we need a way to aggregate by topic, by type of activities, in order to check anomaly per category of purchasing. So we need to build yet another pipeline which does value mapping of the different operations, one-hot encoding, aggregations per type of transaction, and essentially storing the data. Note one thing here, that the data that this feature and feature processing pipeline is storing is not just offline data in Parquet files or in data warehouse. It's also generating the real-time data that will be used for the production, for the inferencing, without any additional work. So when I'm developing that in an iterative fashion in my notebook, it's actually already ready for production. And we're going to see how we use it. So we build those pipelines, and in order to build those into an operational service, after we played and debugged them on our notebooks, it's essentially one click away. I'm just essentially deploy ingestion service, telling it which feature set I want to deploy, and sort of some configuration. And this is actually sort of debug turned on, but it's actually creating a full-blown service at an HTTP endpoint, which is doing the real-time ingestion. I can actually just go and ping that service and ingest data and see how it's working. You see, it's actually I'm ingesting that piece of transaction and getting sort of an ID back, meaning it was ingested. Another thing that I may want to ingest for training is the labeled data set. The labeled data set is also generated from the transactions, because I know if it was a fraud in a certain delay. So if I shift the time of the identification of the fraud, I can actually turn it into a label. This is what this code is doing, is building a pipeline for labeling. And now we have another feature set for labels. If we go into MLRun user interface, we can see all those 4 feature sets that we've created. For example, the transactions, all the features from the transactions, the different transformations we created, the actual data, the statistics of the data, and so on. For every feature that we created, even if we created through a notebook and not through UI or API, we can just see that, and then we can build. You can see all the total features and just create feature vectors from all those different features. And we're going to look into that in a second. So this is how we created a full operational pipeline that ingests from 4 different data sources. Some of them are streams, some of them are batch. You've seen it, it's relatively easy to build all those ingestion pipelines. The underlying engine will be things like Spark or Dask or Nucleo. There are different engines depending on the type of workload you're doing. But all of that is sort of done through a serverless engine. You don't really care. You see, I'm just writing a few pieces of Python code, and there's a serverless engine that transforms it into an operational pipeline. Now let's build the machine learning pipeline, so the pipeline that does the training. So in order to do that, we just create a feature vector. We define which are the features that we want to use for our model. So you see, different aspects of the account transactions, and some features from the events, and other features from the categories, and so on. So we build a feature vector. We can get the feature vector, and you could see it's already, all the feature vector was generated for us, including joins and time travel joins and things like that. So, a lot of work. If you're doing SQL, you do it here in a single operation of just give me the feature vector. All the work is done behind the scene. And now I want to run training. So in order to run training, I'm choosing a pre-baked MLRun function for scikit-learn classifier using scikit-learn algorithms for logarithmic regression. So we have different algorithms that we want to run in sort of an AutoML loop and hyperparameter loop. And it will essentially just go and run the training and respond at the end. It's essentially running it on a cluster on Kubernetes. It responds. You can see the accuracy pretty high. You can see a lot of artifacts that were generated, all the results, and so on. But I don't want to have all those features because I want my model to perform better. I want less features. So some of the things that I can use is use another function in MLRun, which is the feature selection function. Essentially, you give it all the features, it will run some work and prioritize which features have the best impact on your model, and then you choose a subset of those features. So this time I'm using a lot less features, and I'm running the training on a lot less features, and essentially getting still pretty high accuracy. The accuracy here is still, you see, 99 point something %, with half the number of features. That essentially will also reduce the computation effort and so on. So you've seen here how I built all this work of creating a feature vector from the features that came from production, building the training, removing features in order to create bigger efficiency using pre-baked functions, and essentially this is generating the model. Now, if we go into the MLRun UI, we can actually see the training jobs running, or different executions of the training jobs running. And we can see, what was the input. This was the input feature vector. These are the different artifacts that were generated by the training. It has multiple versions. If I run it multiple times, everything gets versioning. So you get the experiment tracking and versioning and all that done automatically for you. Also, the model objects was saved, and we're going to use the model object in our next pipeline. So the next thing is to build the full operational pipeline, as we mentioned, an operational pipeline that intercept calls, run the enrichment, does the model surveying on multiple models, and eventually responds to the user, along with model monitoring and all of that. And so here we're creating a serving class. This is sort of part of the things built into MLRun is a serving engine, which could be customized. You can use off-the-shelf serving functions, but you can customize your own function if you want to do some pre-processing and post-processing and so on. So here we're building a classifier model using the MLRun model server. We need to essentially implement the load and the predict hooks, but here we also do pre-processing hooks, because what we want to do, some of the data may be missing, we may have null values and other things, and we want to do imputing on the values, essentially substitute the values that are missing with average values. Where do we take the average values from? We actually take the average values from the feature store. So here, during the load of the event, we're loading the load of the model. We also load the feature vector into the model server. Then during the processing, we're just injecting the source, like the customer ID, where it enriches the entire vector with all those features that we've seen before. Here there is a loop logic for imputing and replacement of missing values with values from the feature vector object, and then just doing the predict. So relatively simple function that does imputing and other things. And here we're essentially building the topology. This is where we build what we call a graph topology of the. Trying to do this. Yeah, so here we build a graph topology with multiple models. You see, this is with the pre-processing, with the ensemble across 3 different types of models. And then we can even simulate this real-time pipeline by creating sort of simulator, what we call a mock server. We can just see how the feature vector, the feature store works. We can just feed in an ID as a source to the feature vector. And then what you'll see is that the feature store responds with the full vector, and that's done within a few milliseconds. So it's really, really fast and can be done. You can do real-time fraud prevention, not just detection. And then in order to deploy this real-time pipeline, which has data preparation, ingestion, feature enrichment, and model monitoring, everything, we just do deploy. That's it. No DevOps guys, no data engineering guys. I'm just doing deploy, and this is building a real-time function on an HTTP endpoint. If I want to test that function, I'm just doing invoke, and I can see the results of my inferencing pipeline. So what you see here is that we've essentially built the entire flow that I was mentioning. We used the feature store to ingest all those different data sets, We could do data exploration, as you've seen, using Jupyter. We built model development pipelines, and then we built real-time pipelines. Now, all the things that I did could also be automated using, for example, Kubeflow that was mentioned. You could just create a notebook with a pipeline. This is sort of a pipeline telling me, I need to do some ingestion and then training and then maybe evaluation, testing, deployment, just specifying the different steps I need to place on my DAG, on my graph, and then just let it run, and it will run and produce all the results. And I could also trigger that graph, as Greg mentioned, periodically when I need to do retraining and so on. Another nice trick is that I can do the same within a GitLab or GitHub Actions sort of CI systems. And then every time I do like a code change to my code or my data, this can trigger automatic CI processes that will even report back into the CI system, so I can track when I change the code, what was the impact on the accuracy of my model without doing a lot of DevOps work and so on. So with that, that's my part. Again, don't feel afraid to contact us on LinkedIn or Twitter or Slack, and if you have more questions, we'd love to answer them.
Great. Well, I would like to thank the three of you for the great presentation and the very interesting demo. So I think we have probably a little bit of time for a question or two, so feel free to ask your question following the format. Also, David reminded us to fill the poll if you have time, so there is a poll button that you can click and just answer whether you find the session helpful. So don't hesitate to ask a question. There's already has been a question asked by Dane, and I encourage you to read it because I think that Greg already answered the question. Then Shun Wang asked a question. So how is the online feature store connected with real-time data source in this demo? I don't know who wants to take on that question.
Yes, I can address that because it was part of the demo. Essentially, the way that the real-time features are produced is there are real-time serverless functions that are generating the features essentially by compiling this pipeline that we defined in the notebook. It sort of gets serialized and compiled and turns into a real-time data analytics function. And it can listen on many different types of sources, HTTP, Kinesis, Kafka, Azure Event Hub, and so on. So there are about 13 different data sources for real-time, but also sources for batch. You can schedule a job that reads from a database, Snowflakes, Oracle, whatever. And this is actually, Greg is using Snowflakes quite a bit. And you can ingest that data into your system as well.
Any other questions? So on my side, I have one. So when the model starts to outperform over time, so how do you detect that? But also, how do you react to that?
I can take that from our perspective. So we as part of our pipelines, we set up a monitoring component, and we set thresholds for expected values for performance. And then based on those thresholds, we will set retraining, and then we will do an interception to have a human in the loop validate model performance before we redeploy.
Thank you. So I think that's it in terms of questions. So if there is no more question, well, yeah, I think that's all for the questions. So on behalf of the TMLS team and then everyone, I would like to thank again all of you for that very insightful talk. And so I wish you all a great day, and see you in the next session.